The carbon ion of the alkyl lithium and the Grignard can also react with carbon dioxide. This is similar to carbonyls because the lowest structure of carbon dioxide is a C with two double bonds O. This is linear in there. So it's as if like you are working with a carbonyl in there. So these carbon ions can react with carbon dioxide where the carbon of the carbonyl is the electrophilic site, or they can react with the epoxide. Let's consider first the carbon dioxide. So any carbon ion from the alkyl lithium or the Grignard can come attack the carbon of the carbonyl, form a negative charge. It's a two-step reaction. The first step is the addition of the carbon ion to the electron positive site. You have here a nucleophile electrophile reaction. And the reason why this reaction occurs because you don't have any acidic hydrogen in there. So this is why you have a nucleophile electrophile reaction. You are adding to the carbonyl, so whatever R of the carbon ion that you are working with, that is going to be attached to the carbon of the carbonyl. And the other oxygen of the carbon dioxide will turn into an O negative in there. That will be coupled with the positive charge, any positive charge counter ion in the solution. And then the last step is going to be the protonation. So your product in this case is going to be a carboxylic acid. And this is a very good way of introducing a carboxylic acid to your compound. This is called a multi-step reaction. This is step 1, step 2, and step 3. The way that you approach these reactions, you go one step at a time. Okay, and for every step, you write the product for the reaction. So let's go with the step 1. We are doing magnesium in presence of diethyl ether, and this is how we make our Grignard. So remember here we are starting with an Rx. The R over here doesn't matter what R that is. It's an sp2 hybridization. It can be an sp3. It doesn't matter in there. This is how I make my Grignard. So the first step is make your Grignard in there. To make your Grignard, just insert the magnesium between the carbon over here and the bromine. So you're going to end up having an Mg and a bromine in there. Okay. You can take off the bond in here and simply make this one ionic. It's fine. Here you go. This is going to be negative. This is going to be 2 plus. So this is going to be my carbon ion. So now once I have my carbon ion, now I'm going to react with the second step. So this is step 1. Step 2 of the reaction, I'm going to do a carbon dioxide. Remember, carbon dioxide is linear. Please show it as a linear geometry like that. So now my nucleophile is going to come. This is a nucleophile electrophile reaction because the carbon is partial positive. Every time I make a bond, I break a bond in there. So all I did now is simply I added the carboxylate ion to this carbon over here. So this is called a carboxylate ion. I do have my carbonyl over here, the O negative. Okay. So this guy here is called a carboxylate ion. And this is what I added in there. Now, this negative charge is going to be balanced by any positive in the solution in there. And what I have here is the Mg2 plus. Of course, I need to couple that with the bromine to be a total charge of 0. These two are 2 negative, and the magnesium is going to be 2 positive in there. I'm not done yet because this over here, I'm using it with just carbon dioxide. I still need to protonate because every product that you form has to be a 0 charge. It cannot be in an ionic form because if it's in its ionic form, it's not going to be called a product. So now my last step in there, which is the, let's see, it's the H3O plus. So I'm using the H3O plus in there. And this is the last step, which we call a protonation step in there. So with the protonation step, it's going to be an acid-base reaction always. So that's going to be my base. It's going to come and take that acidic hydrogen. Water is going to leave. And in this case, don't forget your benzene. In this case, I will end up forming a carboxylic acid in this case. I just want you to see what we did over here. So we started with a bromine on the benzene. Okay, we did those three steps in there. All what we ended up with is replacing the bromine with the carboxylic acid. Okay, so here my final product is going to be replacing the bromine with a carboxylic acid. So this is going to be the COOH. This is how you write the carboxylic acid in its condensed form in there. You can write it either a COOH or a C double bond OOH. Both are the same. From where did I get this carbon? This carbon is the carbon from the carbon dioxide in there. And this is a good way of replacing the halogen by the carboxylic acid. Another reaction that the carbon ion of the alkyl lithium and the Grignard undergo is the ring opening of the epoxide. This is in basic medium. We did explain this in chapter 8. You already have the video for it, but we're going to go over it over here as well. So because you are working with a basic medium here, how did I know it's basic? I know it's basic because the carbon ion is a negative charge. And if I have a negative charge in the solution, no acid around, then I know that this is a basic medium. If it's a basic medium, then the R, when it attacks the epoxide in there. So over here, these are the two carbons of the epoxide. And we said, if you remember in organic 1, that this oxygen is electronegative. So because it is electronegative, it's going to introduce a direction of polarization in there. So it's going to pull the electrons towards itself in there, making it a negative charge. So each of these carbons is going to be a partial positive charge there. Now, these partial positive charge carbon, they are not the same because this one is less substituted than this one. So it really matters where the R is going to attack. Now, whenever you have a medium that has no acid in it, the R needs room to attack. And if it needs room to attack, then it's going to always attack the less substituted carbon. If you allow the R to attack the most substituted carbon, you're going to end up getting the wrong product. The R always attacks from the opposite side of the epoxide. So if you are having stereochemistry and your epoxide occupies all the area which is in front, then the R has to come and attack from the back just to open this bond over here. These bonds over here, these are very weak bonds. These are made up of the overlap of the sp3 hybrid orbital of the oxygen with the sp3 hybrid orbital of this carbon over here. Because you are squishing all of these two carbons in there that assumingly should have a bond angle of 109.5, and you are squishing it into a 60-degree bond angle, those bonds in there are going to be weak bonds because the overlap between the p orbitals is bent. So this is why we call them bent bonds. Bent bonds are weak bonds. So these weak sigma bonds in there, they can be broken easily. This is why when the R attacks, it needs to attack from the opposite side so that it can break off the cycle. When the cycle is broken, then you will have a second protonation step. This is a must to make your product neutral. So the oxygen in there is going to turn into an OH. Normally, when you are doing stereochemistry, the stereochemistry of the oxygen is going to be the same as that of the OH. So if your epoxide is in front, then your OH at the end will end up to be in front. Always your addition has to be a trans addition because your carbon ion needs to attack on the less substituted carbon. So here it's attacking on this carbon over there. It's going to attack on the less substituted carbon from the opposite side of the epoxide, and it's going to break this bond over here. So the oxygen will stay in front, and that when it's protonated, you are not breaking the chiral center in there. So it stays in front, and you end up having a trans addition in this case. The R can be any R, as we agreed. So it can be an alkyl lithium in this case. This is a carbon ion, it's a triple bond, so it's the same idea. You have a basic medium in this case, no sort of an acid, so that nucleophile is going to come, it's going to attack the less substituted carbon in there and open the bond. If you don't have your epoxide locked in a cycle like this one, you don't have to show the stereochemistry in there, because we know that we have a rotation around the carbon, single bond carbon. So no need for you to show the stereochemistry, and no need for you to show that it is a trans addition. So have your carbon ion attacking the less substituted carbon, open the bond of the epoxide, and pretty much that's it. This means that I would end up having two carbons in there. These are the carbons of the epoxide. So this carbon here and this carbon there, these are the carbons of the epoxide. Okay. And what I added on the carbons of the epoxide is the carbon ion. This is the R from the carbon ion from the alkyl lithium. And that OH is the oxygen of the epoxide that gets protonated in the second step of the reaction.